Okay, hello. This is Physics 2212, Lab 1, and my name is Sean again. Today we'll be going over the charge tape lab, and let's get started. The materials you'll be needing are clear tape, ruler, a flat surface, raised objects for supporting the table, and glow script for computational modeling. The purpose of today's lab is to observe the interactions between charged insulators and to determine the amount of excess charge on each of them. We'll also be determining the number of electrons. So here's a brief overview of our results. When we determined the charge on each piece of tape using the measurements from a floating tape experiment, we received a charge of 1.168 times 10 to the negative 8 coulombs. When determining the number of electrons lost on each piece of tape, we found that there are 7 times 10 to the 10 electrons. This is calculated using the charge on each tape along with the charge of an electron. So let's go over some of the physics that is used in this lab. First of all, we have Newton's second law. Newton's second law states that the system's change in momentum over time is proportional to the force applied. And we can see that in the equation below, F net is equal to change in P over change in T. There is a calculus version of this, but it is not here right now. The second thing that we have been using is Coulomb's law, and this describes the electrical force between two charged objects. Coulomb's law is equal to Fe is equal to 1 over 4 pi epsilon naught, also known as K, times Q1, Q2 over R squared times the R vector. And you can see those right below that equation. The last thing we'll be using is gravitational force to see how much mass This describes the force between two objects with mass, and we'll be using this to analyze the floating tape. Let's go over our initial conditions. The tape's initial mass was 2.5 grams, or 2.5 times 10 to the negative 4 kilograms. The length of the tape was 0.25 meters. The tape's width was 2 centimeters. The tape's area was 0.4 meters squared. The atom's side length was 1 times 10 to the negative 10 meters, which was established in the lab. And this turns out to an atom area of 1 times 10 to the negative 20 meters squared. So we determined the number of atoms in the tape to be 4 times 10 to the 17. Lastly, let's go over our systems and surroundings. We determined our system to be the bottom tape that was forcing the other tape up, and we determined the surroundings to be the top tape as well as everything else. The distance between the tapes when the top tape started to levitate was 2.5 centimeters. So let's go over the calculations. Firstly, we're going to use the gravitational law, which is Fg is equal to mg is equal to this. This is times by the mass of the tape times gravity, which gives us this. Next, we have F net is equal to Fe minus Fg. This is saying that when the tape is levitating, the electric force and the gravitational force is balanced, so we can say that they're equal to each other, which is equal to this. Nextly, we can take the force electric equation and we can isolate it for Q, getting this. This is the charge on each piece of tape. Now, we have the number of electrons lost. We can find this by dividing the charge of the tape by the charge of a single electron, which is the charge that we just found earlier here, divided by QE. This gives us 7 times 10 to the negative 10 electrons. Here's our glow script model that we use to find those calculations. Here's our initial conditions. You can see that I have the length of the tape mass, the tape width, as well as the distance to the tape that we found. This is the actual distance. It says 2.5 centimeters over there. I was just informed by my lab mate that it is actually 2.2. Next, we have the tape objects. We have our sphere, our two spheres representing both pieces of the tape, and we'll go over why we did this later. We have our calculations, which are printed out over here, and our electric field function. So we can see that the force of gravity, as well as all these other forces, match up with the manual calculations that we did earlier. Next, there's our assumptions and our errors. First of all, we assume that there's no air resistance or friction to simplify the calculations to a level where we were able to do them. Secondly, we condensed the tape down to a point charge for analysis. This is why you saw the little spheres over there earlier. We're modeling the tapes as point charges. Lastly, we had assumed that each tape had the same amount of charge and even distribution of charge. This caused a few errors. First of all, we know that there will be an unequal distribution of charge across the tape, depending on how the tape was handled. And this might cause the the tape to generate more force in certain areas than others. Secondly, since we used our hands to handle it, it probably lost a lot of electrons, and this would skew the charge of the tape as well as the number of electrons. The values for those that we got. Lastly, let's get into a bit of a discussion. So what if protons and electrons inverted charges? Honestly, this wouldn't do anything, really. Since we are adjusting the parity of everything, it is the same as nothing changing. It's like multiplying by -1. Like, imagine if the scientists that created this decided that protons were negative and electrons were positive. Really, nothing would change. The second thing, why is it important to handle the tape as little as possible? This is because when it comes into contact with stuff like your hand, it generally tries to neutralize itself. So the more you handle it, the more neutral it's going to get and the less charged it's going to be. This will also skew our numbers. Thank you for watching.